Hello, good morning, my dear lecturer, colleagues, friends, and lovers and well-wishers of chemical science. Here I mean people who love learning, listening, and knowing more about chemical science. Here is the time that we are going to explore more in chemical science, but that is majorly about organic chemistry. Colleagues, friends, and my dear lecturer, my name is Modingi Joseph. I'm a student at Victoria University, and I'm here to make a presentation in one of my coursework assignment in chemical science, and that is all about organic chemistry. In this presentation, friends and colleagues, I'm going to discuss about two topics in chemical science, and these two topics are under organic chemistry. Topic number one is about introduction to organic chemistry, and our second topic will be about hydrocarbons. In these two topics, colleagues, these are the two areas, these are the areas we are going to discuss about. One, in introduction to organic chemistry, we are going to look at the significance of carbon compounds in biological systems and industrial applications. Then in our second topic, which is hydrocarbons, we are going to discuss about the definition of hydrocarbons. What are these hydrocarbons? The classification and the properties of alkanes, alkenes, alkynes, and the cyclic hydrocarbons. We shall also look at overview of polymerization processes and examples of simple polymers. And these simple polymers are usually the natural and the synthetic polymers. We shall also look at the application of organic compounds, uses in the production of plastics, detergents, and the process of saponification. We know that these organic compounds are very vital in our daily lives. And now here we are going to look at how do we use them in our daily lives. Look at the plastics. We use these plastics in our environment, in our homes, and we are yet to know how really are they, where do they come from? They come from these organic compounds. The detergents, some of the detergents, we make them local at home for cleaning. Some of them are bought and used in our homes. The process of saponification. What is this saponification? It is all about the process of making soap. Saponification is all about making soap. So we are going to look at more about it in the next upcoming presentation. We are also going to look at the references where we can find this information that I have put here. So my dear colleagues, friends, we are going to start our presentation. And here is our first topic, which is introduction to organic chemistry. Like I told you, we shall need to know what is this organic chemistry. Organic chemistry, by definition, it is just a branch of it is just a branch or an area of chemistry that deals with the study of carbons and its compounds. We all know that carbon is now known to form seemingly unlimited number of compounds which are impactful in our daily lives. It is impactful in medicine, agriculture, and general life. In a theory that is by Oparin 1923, organic chemistry may have its beginnings with the Big Bang theory, when the compounds of ammonia, nitrogen, carbon dioxide, and methane combined to form amino acids. So an experiment that has been verified in laboratories That is according to Myler 1950. So that is a brief history of organic chemistry. I said earlier that organic chemistry is a branch or an area of chemistry that deals with the study of carbons and its compounds. Let's look at the significance of carbon compounds in biological systems and industrial applications. But beginning with, let's look at the significance in biological systems. Here, when I talk about significance of these carbon compounds in biological systems, I mean how are they used in biological systems. We know that carbons have a unique ability to form four stable covalent bonds with other atoms. This is actually including itself. So this allows for the creation of large, complex and diverse molecules necessary for life. So all life is carbon based. So carbon, we have the macromolecules. Carbon is the primary component of the four major biological macromolecules, and these include carbohydrates. We all know carbohydrates, how important it is in our bodies. So these carbohydrates provide immediate energy, form structural components like cellulose in plants. Then number two, we have the lipids. These lipids are just fats and oils. So lipids store long-term energy, form cell membranes, and those are measured the phospholipids, and act as the signaling molecules, the steroids. Then another carbon compound is the proteins. These proteins perform a vast range of functions, including catalyzing metabolic reactions as enzymes, forming muscle tissue, transporting oxygen in hemoglobin, and providing structural support. Then the fourth one is the nucleic acids. So these nucleic acids carry genetic information, that is DNA and RNA, which are the instructions for any organism's development, survival, and reproduction. So nucleic acid is very important, friends, because as we know, the DNA and the RNA, they are the ones that are in charge of some organism's development, survival, and reproduction. So that means there is no way any organism can develop, survive, and reproduce if there is no those instructions called DNA and RNA. So let's look at these the biological processes. So compounds, these carbon compounds are integral to vital processes such as photosynthesis. We know photosynthesis, that process when plants make their own food. So plants use carbon dioxide from the atmosphere to produce glucose, which is carbohydrates, for energy. Number two is respiration. So organisms break down carbon-based food, that is glucose or carbohydrates, to release energy, producing carbon dioxide as a byproduct. So it uses the oxygen available to produce this energy, or to burn the glucose or the food, the carbohydrates, to release the energy which is needed by the body to function normally. The carbon cycle. Carbon continuously moves through the atmosphere, oceans, soil, plants, and animals, maintaining an essential balance for the planet's climate and ecosystem. Friends, all those are the significances of carbon compounds in biological processes. So we have seen all these biological processes: respiration, the carbon cycle, photosynthesis. All those ones basically need carbon compounds in order to take place. Let's look at the significance in industrial applications. Here we are going to see how are these carbon compounds significant, important in industrial applications. So the versatility of organic compounds, that is now carbon containing compounds, makes them indispensable in numerous industrial sectors. One, energy and fuels. Fossil fuels such as coal, petroleum, that is crude oil, and natural gas are carbon-based hydrocarbons and remain a primary source of energy for electricity and transportation. So, colleagues, those are carbon compounds. They are very essential in energy and fuels. The so-called fossil fuels and natural gas, petroleum, they are all made up of carbon compounds, most of the hydrocarbons, and they remain a primary source of energy for electricity and transportation. This means there is no way you can get this energy. You cannot get electricity. You cannot get electric energy. You cannot get this mechanical energy without some of these hydrocarbons or carbon compounds. We have vehicles, we have motorcycles, we have aeroplanes, tractors, those vehicles, to name but a few. They all work. They get the energy from these hydrocarbons. Then when you look at the plastics and polymers, there is no way you can, friends, have these plastics and polymers when you don't have carbon compounds. So carbon is the backbone of synthetic polymers and plastics like polythene and nylon. So these ones are used in everything from packaging and clothing to automotive parts and construction materials. So friends, there is no way you can construct these nice buildings, carry some other things when you don't have these polymers and plastics. We have seen our houses where we live, the toilets, they are all having these plastics in form of pipes, which are used for fixing here and there to enable the sewage flow. The clothings that we are putting on, they are all products from these hydrocarbons. The pharmaceuticals and medicine. So colleagues, you can see that even the drugs we are using, the medicine we are using, they are all made from these hydrocarbons. So many active pharmaceutical ingredients, the APIs, including common drugs like aspirin and the penicillin, are all organic compounds. So organic chemistry is central to drug discovery and synthesis. We have seen so many people are suffering from many diseases, and up to now some people have actually, the few scientists we have, they have even failed to come up with some of the treatment, the medicine for curing some of the diseases, but at least they have used these compounds, carbon compounds, to come up with at least the preventive drugs. Yes, look at HIV. At least there are ARVs. Someone can survive just on those ARVs, much as the virus is not completely healed or killed, but at least there are those products from carbon compounds such as ARVs, which are given to those patients at least to relieve, at least to reduce the viral load, at least to weaken those viruses, much as they cannot be killed. So these carbon compounds are so vital in pharmaceuticals and medicine. The drugs we normally get to have our bodies healthy are all made from these carbon compounds. So still we can you may find that even in agriculture, these hydrocarbons or these carbon compounds are key ingredients in fertilizers, making of those pesticides and herbicides. Now these ones help to enhance crop yields and protect plants from diseases and pests. I know most of us here in the across the globe, we are all farmers. Much as someone will say, but for me, I'm not a farmer. I'm a doctor. I'm a pilot. I'm an engineer. But I know beside those professions, there is some bit of agriculture that we normally perform in our villages to enhance or to boost our earnings. So the agriculture, there is no way you're going to manage your livestock when you do not have these pesticides, because we know that the vectors will always come, the pests will always come and host, I mean, and have, okay, host, they'll be hosted by these livestock. Look at the sesaflies, the ticks. So when you don't have these pesticides or the acaricides for controlling some of those pests, then you cannot get good yield out of your animals that you are keeping. In agriculture, crop growing, you grow crops without spraying to kill some of the pests and the disease causing organisms, then you'll have done a lot of nothing, because after growing your crops, these pests and the germs will come and they will have to destroy your crops. So the carbon compounds can be used to make some of these chemicals that can help us to overcome some of those challenges, some of those blocks in food production. The fertilizers can be made from these carbon compounds, and these fertilizers can help to improve the facility, I mean the fertility of the soil, so that when our crops are growing in fertile soils, we are able to get good and great crop yields. Materials in material science, these carbon compounds, like right now I'm talking about chemical science, organic chemistry. You may find that some of these various carbon allotropes have unique properties. The diamonds are used in industrial cutting tools due to their hardness, while the graphite is used in pencils, lubricants, and batteries. Friends across the globe, I don't think there is anyone of you who has never used a pencil. For me, right from my lower classes, that is a nursery and a baby class, kindergarten, and a primary 1, 2, I was using a pencil. I even reached an extent whereby I was also asked to use a pencil in P3, much as it wasn't a fun experience for me. So these carbon compounds can be used to make some of those materials. The diamonds can be used to make industrial cutting tools, because for them they are hard. Then the graphite can be used to make pencils, lubricants, and batteries. The carbon fiber composites are used in aerospace and sports equipment for their strength and lightweight properties. So friends, you can see how relevant these carbon compounds are. They can also be used in household products like making soap, detergents, cosmetics, perfumes, and paints. They all rely on diverse organic chemicals for their function and properties. So friends, today you cannot live without soap, without these detergents, cosmetics, perfumes and paints. These beautiful houses we are living in, they are painted, and these paints are coming from these organic chemicals or compounds. The perfumes you apply on your body, on your cloth, and you all smell good. It drains away all the other body odor that may be coming from your body. So the soap, when you are bathing without soap, my friend, the bathing may not be productive, because the germs will remain. You get, so the chemicals which are found in this soap can help to kill germs that may be on our bodies, and this can promote the proper growth of our bodies without any healthy disturbance. So let's also look at hydrocarbons. Colleagues, earlier on I told you this is our second topic, and it is all about hydrocarbons. So we are on introduction to hydrocarbons. I told you, colleagues, that we are going to begin with the definition of hydrocarbons. Here we need to know what are hydrocarbons. What is this we call hydrocarbon? What is it? So a hydrocarbon is an organic compound composed of entirely hydrogen and carbon atoms. So hydrocarbons are just organic compounds composed of entirely hydrogen and carbon atoms. So they form the backbone of many substances like fuels, plastics, and natural gas. These compounds are classified based on their carbon bonds as either aliphatic hydrocarbons, for example the alkanes, alkenes, and alkynes, or aromatic hydrocarbons, which are often contained in a benzene ring. So they exist as gases, liquids, or solids, and their properties are determined by their molecular formula, as we shall see on the next slide. So we are also going to, having known the definition of hydrocarbons, like I've said, hydrocarbons are just compounds made up of hydrogen and carbons. So we are going to classify these hydrocarbons. So here we are, classification of hydrocarbons. So we shall not only look at the classification, but we shall look at the classification and properties of hydrocarbons. And these are majorly the alkanes, alkenes, alkynes, and the cyclic hydrocarbons. We have discussed this already. What are hydrocarbons? We said these are compounds composed of exclusively hydrogen and carbon atoms. So primarily sourced from crude oil. So the way carbon and hydrogen atoms bond determines the class of hydrocarbon and its property. I think that is clear. The way the way the carbon and hydrogen atoms bond together determines the class of hydrocarbon and its compound. So classification of hydrocarbons. We have a flow chart. I was not able to draw this flow chart well, but at least I will explain and we understand. Hydrocarbons, like we saw earlier, we said it is classified into two. One, we have what we call the aliphatic or the non-aromatic hydrocarbons, and then the second one is the aromatic hydrocarbons. And we said the aromatic hydrocarbons contain the benzene rings. So it is also benzene rings hydrocarbons. Then the aliphatic or the non-aromatic hydrocarbons, They are also classified into two. They are classified into the saturated aliphatic hydrocarbons and then the unsaturated aliphatic hydrocarbons. So the saturated aliphatic hydrocarbons include the alkanes and the cycloalkanes. Then the unsaturated ones include the alkenes and the alkynes, as we shall see on the next slide. So let's look at the saturated hydrocarbons, and we say these are majorly the alkanes. So by definition, saturated hydrocarbons are hydrocarbons with only single covalent bonds between carbon atoms. Like you can see, C has got a single covalent bond with the other carbon atom. So the general formula for this alkanes is CnH into bracket 2n plus 2, whereby the n stands for the number of carbon atoms, and then the hydrogen atoms will be got by multiplying 2 times the number of the carbon atoms, then plus 2. The properties of these saturated hydrocarbons. So they are relatively unreactive, and they undergo combustion and substitution reactions. Boiling points and viscosity increase with the chain length. So as their boiling points and viscosity usually increases with the chain length. How long these carbon atoms are with their covalent bonds determines the boiling points and the viscosity of these hydrocarbons. What are the examples of these hydrocarbons? One, we have methane, which is CH4, and then we have ethane, which is C2H6. Methane, we have said it is CH4, meaning it has 1 carbon atom and 4 hydrogen atoms. Then ethane is C2H6, meaning it has 2 carbon atoms and 6 hydrogen atoms. So the visual display of the structure formulas for methane and ethane. Was I unable to draw it due to some inadequacies in typesetting. The saturated hydrocarbons, and these are now the cycloalkanes. By definition, these ones are defined as the saturated hydrocarbons that form a closed ring structure. So the general formula is CnH2n, that is for a single ring. What are their properties? These cycloalkanes have the following properties. One, they are similar to alkanes, but with slightly different physical properties due to their cyclic shape. Like we said, for them, they have a closed ring structure. So that is where they differ from the alkanes. So what are the examples of these cycloalkanes? One, we have the cyclopropane, we have the cyclohexane, and others. So let's also look at the unsaturated hydrocarbons, and these ones we said we have the alkenes and alkynes. So by definition, these are the hydrocarbons containing at least 1 carbon-carbon double bond, as we have seen in that structure. That is C, it is having a double bond with another carbon atom. So the general formula for this one is CnH2n, meaning it will be determined by having the number of carbon atoms, which will be now, and the hydrogen atoms will be 2 times the number of carbon atoms for one double bond. So the properties, they are more reactive than alkanes due to the double bond. We said alkanes are reactive, but these ones are more reactive because for them they have what? A double bond. Then they also undergo addition reactions where the double bond is broken to add other atoms. For example, when you look at ethene, which has 2 carbon atoms and 4 hydrogen atoms. Then propene, which has 3 carbon atoms and 6 hydrogen atoms. So those were unsaturated hydrocarbons, the so-called alkenes. Yes, the so-called alkenes. So let's look at the unsaturated hydrocarbons, which are alkynes. Now, by definition, these are hydrocarbons containing at least 1 carbon triple bond. So these ones are having carbon triple bond, not a double bond like it is shown here. It has to be a triple bond, which means there will be 3 equal signs there. 1, 2, 3. So I've left out 1 there, I've omitted it, but that is how it is. So these unsaturated hydrocarbons, the alkynes, are major hydrocarbons containing at least 1 carbon triple bond. So the general formula will be CnH2n take away 2 for 1 triple bond, whereby, like I said, the N stands for the number of carbon atoms. So the properties of these alkynes: 1, they are very, very reactive due to the triple bond that they hold. The number 2, they also undergo addition reactions like the alkenes. Then examples include the ethane, which is also the acetylene, which is with a chemical formula of C2H2, meaning it has 2 carbon atoms and 2 hydrogen atoms. So the visual presentation of this formula, or the structure formula of ethane, is H single triple bond. So it is H minus C, H dash C, then a triple bond there, then a C dash H. That is its structure formula. So this indicates that ethane has 2 carbon atoms joined by a triple bond. I think that one is clear. Yeah, H dash C triple bond dash hydrogen atom. It shows that ethane has 2 carbon atoms, like we are seeing 1, 2, and then and these 2 are joined together with a triple bond, as we have seen in our structure formula. To proceed, we are now going to look at the other type of hydrocarbons. Remember, the first one was the aliphatic hydrocarbons. Now the second one is the aromatic hydrocarbons. Remember, the aliphatic hydrocarbons, we say they can also be called non-aromatic hydrocarbons. We have seen what they are. Now we are looking at the aromatic hydrocarbons, and now these are carbon compounds. These are organic compounds composed of hydrogen and the carbon atoms that contain at least one stable planar ring with localized electrons, a structure known as the benzene ring. So these aromatic hydrocarbons can also be called the benzene ring, because they are composed. They are just organic compounds composed of the hydrogen and carbon atoms that contain at least one stable planar ring with delocalized electrons. I beg your pardon. I say aromatic hydrocarbons are just organic compounds composed of hydrogen and carbon atoms that contain at least one stable planar ring with delocalized electrons. So in a structure known as the benzene ring. So this unique structure, which can be visualized as an alternating double and single bonds, gives these compounds special stability. So these aromatic hydrocarbons are stable, just like you see the benzene ring or the benzene. So leaving that aside, let's look at an overview of polymerization. Friends, you can also say the word is polymerization. Say with me, polymerization. Now, what is polymerization? By definition, polymerization is the process of linking small molecules called monomers into long chains called polymers, so which are found in both natural and synthetic materials. We are going to look at these materials, the natural and the synthetic materials. So we have two types of polymerization, and these are all processes under polymerization. So these two types include addition polymerization and then condensation polymerization. Now, what is the additional polymerization? This is where monomers join without the loss of atoms. So in addition polymerization, monomers join without the loss of any atom. That is addition polymerization. Then condensation polymerization is where smaller molecules like water are released as a byproduct. So in condensation polymerization, small molecules are released as a byproduct. Like the way you see the word condensation, we know, you all know what condensation is in just our local setting. The process in which a liquid or water turns into, a gas turns into water. That is condensation. So in condensation polymerization, you realize that smaller molecules are released as a byproduct. So when carrying out this process, you realize that water is going to be released as a byproduct. So the polymerization processes, I've talked about them earlier. We said they were the types of polymerization. So these polymerization processes are two, like I told you earlier when we were looking at the types of polymerization. So one is addition polymerization, and the other process is called the condensation polymerization. Now, like I said earlier on, addition polarization involves monomers add to one another in a chain reaction without the loss of any atoms. So during addition polymerization, these monomers add to one another to form in a chain reaction, but without losing any atom. For example, polymerization of ethene to form polythene. to form polyethylene. So in condensation polymerization, the monomers join together by forming a covalent bond, releasing a small molecule such as water in the process. So we say the water, a small molecule such as water, is released as a byproduct. That is the condensation polymerization. For example, formation of starch from glucose monomers releasing water molecules. That is the example of condensation polymerization. Formation of starch from glucose monomers releasing water molecules as a byproduct. So those are the two processes of polymerization, which you can also call the types of polymerization. We said in addition polymerization, here the monomers add to one another in a chain reaction without loss of any atom. Then we gave an example of ethene, polymerization of ethene to form the polyethylene. Then in condensation polymerization, we said the monomers join together by forming a covalent bond, releasing a small molecule such as water in the process as a byproduct. For example, we have said that during the formation of starch from glucose monomers, releasing water molecules as a byproduct. So, let's look at the simple polymers. And these simple polymers, like in the introduction we said, they include the natural polymers and the synthetic polymers. Now, the natural polymers, what are they? These are the polymers that usually occur in nature and can be extracted, and they are usually water-based. So these natural polymers are usually water-based. For example, when you look at the cellulose, a structural polysaccharide made of glucose monomers that forms the cell walls of plants. Then when you look at the proteins as natural polymers, for them they are polypeptides made of amino acids monomers. They are just polypeptides made of amino acid monomers. They are essential for biological structures and functions. For example, the keratin in hair and nails, then silk. How about starch? Starch is also a polysaccharide made of glucose monomers used by plants for energy storage. So that is starch. And then nylon is usually a synthetic polymer that is a type of a polyamide. So it has high strength and is used in textiles, ropes, and engineering parts. How about the synthetic polymers? Synthetic polymers are human-made materials formed by chemically linking small repeating units called monomers, typically derived from petroleum. So those are synthetic polymers. They are just human-made materials, and they are usually formed by chemically linking small repeating units called monomers, typically derived from petroleum. So examples of these synthetic polymers include: 1. Common plastics like the polyethylene in plastic bags and bottles. Then we have the polypropylene in containers and packaging. That's where we use those the polypropylene. Then we also have the polyvinyl chloride, the vinyl chloride, that is PCV, like in those pipes for transporting water used in used in our toilets when you are connecting those swages, and window frames. So other examples are the nylon, that is in textiles, polyester in clothing and also bottles, and then the polystyrene in foam cups and CD cases. So this is the summary of the hydrocarbon classes. We have the class bond, the type, general formula, example. For example, the alkanes, we have those with the single bonds, and the structure formula, the methane, it's a formula. Then we talked about the cycloalkanes. They also have a single bond but in a ring. The structure formula is there. Then we had an example which is now the cyclohexane. Then the alkenes, at least for them, they have one covalent bond, one double bond, and the formula is there. For example, the ethene, its formula is there. Then the alkynes, for them, they have at least one covalent bond in a triple bond. Then topic 2, we were looking at the organic, we are going to look at the organic, we looked at the organic compounds. So next, let's look at the applications of these organic compounds. Now, when we talk about applications, we are meaning how can we use them in our daily lives. Now, here is where we are also going to look at saponification. Like earlier on, I told you that saponification is simply the process of making soap. So when it involves the hydrolysis of fats and oil, and these are usually triglycerides, with a strong alkali, for example the sodium or the potassium hydroxide. So the hydrolysis of fats and oil and with these alkali, such as the sodium hydroxide or potassium hydroxide, these ones results into the formation of soap, and that is what we call saponification. So the reactants are usually the fats or oils, the triglyceride, which is also an ester of glycerol, and 3 fatty acids. Then alkali, which is now the sodium hydroxide or potassium hydroxide. Now this one is for hard soap. So the sodium, the hard or soft soap. Now when we use sodium hydroxide, then we shall be making the hard soap. Then when we use potassium hydroxide, that is when you're making soft soap. So the products, we have soap, and this is just fatty acid, salt, and glycerol. The chemical equation, it is a triglyceride plus sodium hydroxide resulting into glycerol plus the fatty acid salts, which is now the soap. Application of these organic compounds still in the process of saponification. One, we have the acid salts, which is now the soap. So the main organic products of the reaction are the sodium or potassium salts of the long chain fatty acids. These molecules have a dual nature. They have a long nonpolar hydrocarbon chain that attracts oil or grease, and a charged water soluble, which is hydrophilic. Then the carboxylate end, allowing them to act as effective cleaning agents. So organic compounds in plastics. Here we need to know what a plastic is. But plastics are polymers which are large molecules made of repeating smaller units called monomers. So those are plastics. So when you see these plastics, they are just polymers which are large molecules made of repeating smaller units, which are also known as monomers. Now you could be asking yourself, what are monomers? Because we have been talking about monomers. Monomers, what are they? Monomers are just small organic molecules that are linked together in long chains through a process known as polymerization. So those are monomers. They are just small organic molecules that are linked together in a long chain or in long chains, and they are usually linked through a process known as polymerization. So uses of plastics. One, we use them in packaging. These plastics are used in packaging. When you go to a shop to buy something, they will pack it in these plastics. They can be polythene bags, they can be a number of things, they can be even containers. So they are used in packaging. Then number two, they are used in construction materials. They are used as construction materials. For example, the PVC pipes, those pipes which are used when you are connecting the sewage, the toilet, and so on within your house. Those are all plastics. Then they can also be used in automotive parts, for example, the electronics. Then organic compounds in detergents. How do we use these organic compounds in detergents, in making detergents? Here we shall also need to know what is a detergent. These detergents, we know they are also used as soap, but for them they are, can I say they are a bit stronger because they are applied in areas where really you look at the sanitation is not good. You can use these detergents to clean effectively, and then they leave the surfaces when they are at least the smell is there is change in smell. The smell which literally was smelling poorly, it now changes the smell and smells according to the detergent used. So detergents are cleansing agents that, unlike soap, work effectively in both hard and soft water. So for them, they are not like soap. We know that sometimes soap in hard water it may not form foam, and in some soap we can only form foam in soft water. So but for them, the detergents, for them, they are effective, they are stronger, so they can even form what? They can produce foam even in hard water or soft water. So these detergents have a non-polar hydrocarbon tail and a polar water-soluble head. So cleansing action, how do we use them in cleansing? The non-polar tails attach to grease and oil. The polar heads remain in the water, lifting the dirt away. So that is how these detergents help to clean. You apply them on a stain, and then they do away with a stain, whether in a cloth or on the floor or in a toilet, very fast because of their effectiveness. Then some of the uses of detergents. One, at home. One, they can be used in laundry, that is washing, then dishwashing, and then industrial cleaning parts. So in industries, those machines in industries, we can use these detergents. Diagram showing how a detergent molecule interacts with both a grease particle and water. This diagram is missing, but it is there. So let's look at saponification versus detergents. Now, when we talk of the saponification, we are talking about soap. So the soap, natural, biodegradable, forms calm in hard water. So react with calcium and magnesium ions. Then the detergents for them, they are synthetic. They are man-made, okay? So they work well in hard water and do not form what? Scum. For them, they don't form scum. But the soap, for them being that they are natural, that means they are from they are from the biodegradable materials, and then for them they form scum even in hard water. So that means they have the ability to react with calcium and the magnesium ions. But with the detergent, for them they are synthetic, meaning they are man-made. Then they work well in hard water and they do not easily form what? Scum. So those are detergents versus saponification. So we can proceed a simple comparison table highlighting the differences between soap and the detergent performance in hard water. So that table is also missing. However, in conclusion, we can say that hydrocarbons, the so-called alkanes, alkenes, and alkynes form the basic backbone for countless organic compounds. So all these compounds that we know come from, or they are got from, hydrocarbons. Applications. The properties of organic compounds stemming from their unique structures also allow for their use in essential products like plastics, soaps, and detergents. So note, organic chemistry is the fundamental to understanding the materials and substances that shape our daily lives. So all those materials we use in our daily lives to look better are coming from organic chemistry. So friends, we can see that organic chemistry is very important, and without it we would be living a very hard life. So these are some of the references that you can use in case you need to get more information about what I've been discussing about. So friends and colleagues, that is all about the two topics that I told you that they are the ones I'm going to present as we saw in our table of content. So colleagues, I want you, if possible, you can give any form of guidance, any feedback you feel appropriate. Please, I welcome it. Can be through inbox, it can be through the platform that is available for you. Yeah, but I need the feedback, at least colleagues, from you people. Thank you for watching. This is once again chemical science, and it is my assignment coursework number 2 about organic chemistry. And the two topics I discussed were introduction to organic chemistry and hydrocarbons. Thank you so much for listening. May God bless you. Thank you. Bye.